Today we discuss one important topics related to measure theory, especially in LP space. Okay, we write it here LPE. Okay, LPE equal to here A belongs to f of E R cos R. Okay, such that f is P integrable. F is P integrable f is p-integrable measurable function on E. Okay, then what happened? Then we have to show that we have to show that LPE be a linear space. Okay, obviously be a linear space over E. We saw it in previous class. Okay, so today we discuss not this one is linear space. We have to show that this one, okay, this one obviously satisfied some, that means norm function. Okay, this one satisfied some norm function or some semi-norm on LPE. If this one norm is not, that means happen, then this one become a semi-norm function. Okay, that means semi-norm function space. Okay, so how we develop this one, we write here in this way. Let P obviously belongs to close to 1 plus infinity, then X a mu be a measure space or measurable space. Okay, then LP be the set of all linear space of P integrable measurable functions on E. Okay, and then define NP, some norm NP, where LPE to 0 plus infinity by here NPE, sorry, NPA here, because NP satisfies those functions. NPA is domain function, this one LPE is domain, so NPF equal to integration E mod f whole to the power P d mu whole to the power 1 by P. Okay, for all f belongs to LPE. Then what happened? Then we have to show that this, then NP be a semi-norm. I have to show that. Okay, so we discuss today this one. Okay, we erase our portion, then going to further discussion of that. We write it now by definition of NP. By definition of NP, we get NPF greater than equal to 0 for all f belongs to LPE. Okay, and second portion is that here NP alpha f equal to what? NP alpha f, where alpha belongs to K and f belongs to LPE. Okay, then this one equal to alpha f whole to the power p d mu whole to the power 1 by p. Okay, then this one equal to integration alpha to the power p f to the power p d mu whole to the power 1 by p. This one equal to what? This one equal to alpha p whole to the power 1 by p integration of e mod f whole to the power p d mu whole to the power 1 by p equal to what? Equal to mod alpha in p f. Okay, then what happened? Then we get this one np alpha f equal to mod alpha npf. Okay, now we erase that portion and going to further discussion of that. Okay, number third, triangle inequality. How we prove this one? Let AFG belongs to this LPE. Okay, then what happened? Then obviously we write it now a plus g. Okay, np f plus g equal to what? Mod of f plus g whole to the power p d mu whole to the power 1 by np yes, np f plus g equal to this one. Okay, this one whole to the power 1 by p, this one less than equal to integration e mod f whole to the power p d mu whole to the power 1 by p plus integration of e mod g whole to the power p d mu whole to the power 1 by p. Okay, this one happened. That means how this one happened? We write it here by Minkowski inequality. Okay, Minkowski's inequality. Also prove this one in previous class, and today we also utilize here. Okay, now we're going to be this one equal to what? npf plus this one equal to npz. Then what happened? Then this one npf plus z less than equal to npf plus npz. Okay, then what happened? Then np be a semi-norm on LPE. Now we write here p belongs to close to 1 plus infinity. Okay, and obviously we prove np be semi-norm on LP. Okay, so now we're going to further discussion of that. That means definition of LP. We're going to LP. Okay, now which one is LP we also discuss today. That means now we're going to the script LP. Script LP means the set of all p integral functions. Okay, but now we're going to LP. LP is what? So we define a relation. Okay, or define a relation, this one by delta y. This one is above then delta, then here we write in this way, just one symbol. F tilde Z equal to F equal to Z mu almost everywhere on E. Okay, then what happened? Then this one we from a equivalence relation. Okay, and how this one from equivalence relation? That means this one is too easy. We'll not discuss more, but if now we discuss here. Okay, F equivalent to F implies and implies by F equal to F mu almost everywhere on E. And if Z, this implies and implies by F equal to Z mu almost everywhere on E. This implies and implies by G equal to F mu almost everywhere on E. This implies and implies by Z tilde F. Okay, again, and what? F tilde Z, Z tilde H. This implies and implies by F equal to Z, Z equal to H mu almost everywhere on E. This implies what? This implies and implies by F equal to H mu almost everywhere on E. This implies what? This implies F tilde. This implies and implies by F tilde H. So mu is symmetric, mu is tangential, mu is mu not. This tilde is symmetric, tilde is tangential, and tilde is reflexive. Okay, all are done. So this one from a equivalence relation. So we write it here. This delta is an equivalence relation. Okay. Now what happened? Now we write here for F belongs to LPE. This one the set of all integral functions on E. Define an equivalence relation. An equivalence relation. Okay. Or defines, not right here equivalence relation, equivalence class. Okay, so equivalence class or cosets. What type of cosets? This F equal to such that Z belongs to LPE, those integral functions such that F equal to Z mu almost everywhere on E. Understand or not? I think all I understand this. Then what happened? Then we define LP, LPE, not the script LPE. This one is LPE. Okay, how we define it? We write it now. Let LPE denote all the equivalence classes, all the equivalence classes of elements of script LPE. That means set of all pair-integral functions. Okay, then LPE denote the equivalence classes of elements of script LPE. Okay, now we erase that portion and going to further discussion of that. Okay, we write it now. Here if here Z belongs to LPE. Okay, then what happened? Then obviously F plus G equal to, okay, F plus G, this one, and obviously this one belongs to LPE. Okay, and how this one happened? here alpha if this one equal to alpha if for alpha belongs to A and F belongs to LP. So how this was happen? You also talk about this one F plus Z equal to F plus Z equal to H. Here F equal to H, Z equal to H1. Okay. Then H equal to obviously H1 plus H2. I understand. In short, we discuss this one. Okay. How F plus Z equal to H mu almost everywhere on E. Okay. And here this one equal to F equal to H1 mu almost everywhere on E. And G equal to H2 mu almost everywhere on E. So we put here H equal to H1 plus H2. Okay. Here A plus Z equal to here A plus Z mu almost everywhere on E. Then this implies this part implies this one. Any problem? I think not a problem at all. Okay. And obviously we erase that portion and going to further discussion of that alpha if okay yeah alpha if equal to some k mu almost everywhere on E and this one if equal to H mu almost everywhere on E, then what happened? Alpha is equal to K. Okay, and obviously this implies that alpha if equal to here alpha is alpha dot if. Okay, yes, that means this one. Okay, not a problem at all. So this one happened, then this one equal to this one mu almost everywhere on. Now we're going to discussion about that. We erase that portion and going to further discussion of that. Hence LPE be a linear space over R. Okay. Now what happens? So some observation is needed here. Okay. We write it observations. If E to R be measurable and integral, this implies, and again if measurable and integral and if belongs to L1E. Okay, this implies what? This implies integration of E mod of f d mu equal to 0. This implies and implies by f equal to 0 mu almost everywhere on E. Okay. Now we erase that portion and going to another observation. Okay. Let a and be a sequence in this collection. Then x, this mu, be a measurable space. Be a measurable space. Then what happened? Then first, if an is monotonically increasing, is monotonically increasing, and then what happened? Then limit n tending to infinity, mu of an equal to mu of union n equal to 1 to infinity an. Okay. Number 2, if an is monotonically decreasing, then limit n tending to infinity mu of an equal to mu of intersection of n equal to 1 to infinity an with mu a1 less than plus infinity. Okay. Now we also discuss this portion, and now going to discussion of another one. This one is LPE norm P be a norm space. We discussed today. We erase that portion and going to discussion of that. Okay. So we write it now here. We write it here. Let P belongs to 1 plus infinity and x a mu be a measure space, be a measure space, and E belongs to this A, and LPE be the linear space of equivalence classes of elements, equivalence classes of elements of LPE. Define norm P here. LPE to 0 plus infinity by norm of AP equal to integration of E mod of AP d mu whole to the power 1 by P equal to norm of F LPE. where f belongs to this LPE. Okay, understood or not? I think all are understood. Okay, then what happened? Then what happened? Then LPE norm P be a normed space. We now erase that portion and going to prove of that. Okay. Now obviously by definition of norm P we get norm AP greater than equal to 0 for all f belongs to LPE. Okay, understood? And this implies, okay, this implies that here this one P sorry uh, okay, this one is, I think this one greater than equal to 0, not this one is right, I think. Yeah, for all this belongs to LPE. Okay, so here I think this one is LPE. Okay, then next, then obviously let this one, this A belongs to LPE. Okay, then norm of if P equal to 0 implies and implies by E mod A whole to the power P d mu less than equal to 1 by P equal to 0. This implies and implies by integration of E mod of f to the power P d mu equal to 0. Okay, this implies what? This implies and implies by f equal to 0 mu almost everywhere on E. Okay, this implies and implies by this one equal to this one. Okay, now here f belongs to this one, then not a problem at all. Then it's p integrable functions, and this implies that this one equal to greater than equal to 0. Okay, then what happened? Then obviously we we that means do this one. Yeah, here norm of if p equal to 0, okay, implies to by this one equal to this class f equal to 0, okay, or 0 class. Then again here it is that portion and going to further discussion of that. Second thing, okay, norm of alpha f, they are class equivalence class of alpha f and norm with respect to norm p equal to what? Equal to integration alpha f whole to the power p d mu whole to the power 1 by p, okay, where alpha belongs to k and a belongs to here lpe, okay, and this f equal to lpe, okay. Then this one equal to what? E mod of alpha whole to the power p mod of f whole to the power p d mu whole to the power 1 by p equal to mod of alpha integration of e mod of a whole to the power p d mu whole to the power 1 by p equal to what? Mod of alpha norm of a p, okay. I think not a problem at all. Next we also discuss that portion here, triangle inequality, okay. Then we let this f g class of f and class of g belongs to this lpe, okay, and note that this f plus g p equal to this one a plus g p equal to integration of e a plus g to the power p d mu whole to the power 1 by p, okay. Then we use here Minkowski inequality. This equal to this one p plus this class of gp, okay. So what we get this one a plus g class, okay, and P equal to this one, A plus C, P less than equal to norm F, P plus norm GP. Okay, for all if G belongs to LPE, the set of all P integral functions. Okay, then what we get? We get here LPE norm P be a norm space, be a norm space. Okay, so we also proved that means the equivalence classes of elements of LPE script LPE equal to LP. Okay, LPE, that means this LP space and this LP space with respect to norm P be a norm space. Okay, then we also going to discussion of some convergence of sequence, but this one is later. Today I stop here. If you get in this type of video, please subscribe my channel, and if you give like, please, and if you have any questions, please write it in comment box, and any suggestions, write it in comment box. So today I stop here.